Hello, hi there, welcome back. One thing we're going to be doing when we label forces, not just use an arrow, but at least for the beginning, we're going to use this format called the type feeler and dealer. So there'll be the force and then the type of force, friction, normal force, gravity, etc. The object which the force is on, and the object which is the giver of that force, the dealer of that force. So for example, if we talk about the force of gravity, there's F sub g. G is our type. Okay, the feeler of the force is the diver, the skydiver, and the dealer of the force of gravity is the Earth. Okay, so that's our first force type, is gravity, and it's always labeled as an arrow drawn down. The second type of force we're going to look at, also really common, is what's called the normal force. And this doesn't mean your average, everyday, typical normal force. Normal in this case means perpendicular. I don't know if you've heard two lines being normal as another way of saying that they're perpendicular, but it's another way of saying things are perpendicular. And the normal force results from two objects in contact. And the normal force is a perpendicular force away from the surface of contact. So if we've got a force of gravity down and the elephant isn't moving, we know from before that there's got to be a force that's canceling that, and that would be the normal force, the contact force on the elephant by the pedestal. Okay, so we're not doing anything too tricky, I don't think. I guess I should be in slide mode. So again, the normal force is always perpendicular to the two surfaces in contact. So even if they're kind of slanted, that normal force slants with it. So again, forces that are equal and opposite in directions cancel. We know that the forces are balanced on the elephant if he's stationary, which he looks like he's stationary, although I don't know how he is. I don't think he can balance like that, but so we say that the net force is 0, or the sum of the forces is equal to 0 when the forces are balanced, or they're equal and opposite. All ways of saying the same thing. Now, on this diagram with the arrows, to show that two forces are equal in length or magnitude, we don't just draw them the same length, because they could be slightly different. You use hash marks or hatch marks to denote that fact that they have the same magnitude. So if I take the perspective of this little blue barrel and I look at it, well, the forces on the blue barrel are balanced. Okay, there's gravity acting on the blue barrel, so there's a force of gravity down on the blue barrel by the Earth. Okay, there is also an upward force, and this is going to be the force of tension. And this is always just going to involve a rope, a cable, something like that. So tension forces will just involve ropes or cables as far as we're concerned. They don't have to, but they will for us. And so the tension is always a pull in the direction of the cable. So in this case, the blue barrel is being pulled upward by the cable. So there's a force of tension on the block by the string. Another very important force is friction. Friction is a contact force, whereas gravity doesn't have to be. For example, friction is a contact force, and it is opposite motion or impending motion. So this baseball player is sliding to the left. Since he's sliding left, friction acts opposite of that to the right. So, and the symbol for force for friction is F sub F. So there's a force of friction on the baseball player by the ground or dirt or earth or whatever you want to say. So now by motion or impending motion, this crate is not moving. Okay, is friction involved? Would there have to be friction? Yeah, if there was no friction, it would slide down. So the opposite impending motion means that since it would slide down the slope, friction is acting upwards to the slope. Okay, so there's a force of friction on the crate by the incline, and there's more. There'd be a force of gravity down and a normal force pointed perpendicular. We just didn't show those. So when we have force left over, we say that's the net force, okay? Or it could be a zero net force too, but forces that are not in equal magnitude and opposite direction, there is force left over. There is a net force left over. So we'll start out pretty basic here. What's the net force on the left here? My net force would be 5 newtons down. Then on the next one, 5 newtons right or up. And the next one, 25 newtons down, and the next one we have to use Pythagorean's theorem, but it's 18 newtons at a certain angle, which we could use sine, cosine, tangent to figure out. Okay, so let's say we've got a ball that's rolling to the right, and I apply a net force of an unbalanced force to the left. What happened to its motion? You didn't see that. Okay, a force opposite the motion of an object slows it down. Okay. If I push something the way it's moving, then it speeds up. And which way do I push something to get it to turn? I push perpendicular to the way it's moving. Okay, and that causes it to change its direction of motion. Now, if we've got an object that has two balanced forces acting on it, and it starts out stationary, when I apply these two balanced forces, let's say there's 5 newtons to the right, 5 newtons to the left, what's going to happen to the motion of that object? Nothing. Okay? It takes an unbalanced force. Balanced forces do not change the motion of an object. It just keeps doing whatever it was doing. So if it was stationary, then it just stays stationary. So for example, let's say we had a ball that was moving to the right, and now I apply these balanced forces, 5 newtons to the left and 5 newtons to the right. What's it going to do? Is it going to come to a stop quickly, gradually, or just keep moving? Well, it's going to just keep moving. Balanced forces it's as if there were no forces at all acting on an object. It keeps moving in a straight line. So to simplify our discussion of forces, we're going to use what's called a free body diagram or a force diagram, whatever. Basically, you look at an item of interest. In this case, it'll be the boy, and you turn the object of interest into a dot. Okay, so the boy's a dot. And then you label the forces. You always draw the forces away from the dot. Okay, so what are the forces acting on the boy? What's a force acting on the boy? Well, okay. One way of looking at it is you draw a box around the boy and you label any forces that are going through the box. I forgot about that. Gravity. Gravity's going through the box. Okay, the Earth's pole travels through the box. The normal force, there's a contact force, okay, pushing the boy upwards. Okay, and to show that those are equal, what do? We use hash marks. So, and again, there's a force of gravity on the boy by the Earth, and there's a normal force on the boy by the pillow. Now, if he's just balanced, if he's stationary, then all the forces have to cancel out. So, and right now my forces cancel, so I'm good. That's how I knew to put the hash marks, is because he was stationary. And a side note, the feeler of all the forces on your free body diagram should be the same. So force of normal on the boy, force of gravity on the boy. All the forces should be acting on the same object, never mix. So let's look at we've got a wrecking ball, and are the forces on the wrecking ball balanced or unbalanced? It's motionless. Well, it would be balanced. So the sum of the forces have to equal 0. They have to cancel out. So forces that are acting on my wrecking ball, if I draw a little box around it, forces that are going through the box, there would be a force of gravity on the wrecking ball by the Earth, okay? And there would be a force of tension on the wrecking ball by the cable. Okay, and am I missing anything? Well, to show that these forces are balanced, I want to use hash marks. Okay, that removes any question of whether or not one's longer than the other. Okay, let's say that it was moving upwards at a constant speed. So I had the cable, the motor running, and the cable was moving upwards at a constant speed. Would the forces on the wrecking ball be balanced or unbalanced? Upwards at a constant speed. The key word here is constant. Okay, it's moving at a constant speed. So that means that the forces on it are balanced. So even though it's moving upwards, the forces on it have to be balanced. So I would use my hash marks again. So anytime the motion of an object is constant, the forces are balanced. Let's look at another scenario. Let's say it was moving downwards at a constant speed. How would I change my force diagram? The answer is I wouldn't. It's moving at a constant speed, so the forces on it have to be balanced. Okay. Let's say it was moving upwards and increasing speed. Okay. Well, if it was moving upwards and getting faster, I know then that force has got to be in the direction of motion. So which one do I need to make longer? The tension force. Okay. These forces do not cancel out. They do not balance. Okay. Normally I would do a demo there, but I'm not doing that. So again, hold up. So let's say we had two masses and they were attached by a string over a pulley. We had a smaller mass, little m, and a bigger mass, capital M, and I released the masses. The big one's going to fall down, the little one's going to go up. If I were to put a force diagram for the big mass, and I were to draw the force of tension, would I make it bigger or smaller than the force of gravity acting on the mass? Well, I should make it smaller because it's going down. Okay. Now, this is kind of a little goofy here that I did that. Now, if we look at on the other side, okay, the mass is going to accelerate upwards, so the force of tension is greater than the mass, the force of gravity acting downward on it. So it's going to accelerate upwards. So, but these two force of tensions would be identical because it's the same string. We're not going to mix free body diagrams like this in the future, so you can kind of ignore that example like that. But the tension would be equal. If an object is at equilibrium, its motion is not changing, which means it's stationary or moving at a constant speed. So we know that the ups and downs cancel and the lefts and rights cancel. And if you want to show that up and down are equal and left and right are equal, but left and right aren't exactly equal to up and down, then you use double hash marks. It doesn't matter which you use double hash marks for. So if the forces cancel, okay, if all the forces balance, ups equals down, lefts equals right. So here the forces do not balance. There is a net force, and it would be a net force downward, of course. And if the object was moving upward and had this force diagram, what would it be doing? It would be slowing down. Now, if the object was moving downward and had this force diagram, it would be speeding up. Okay. What about this one? The up and down cancel, but there's an unbalanced force acting to the right. So if it was moving to the right, then it would speed up. If it was moving to the left, it would be slowing down. So here we've got a force diagram that we want to draw for a diver or a baseball player who's sliding and slowing. Okay, so we know that there's going to be friction. We talked about that before. There's a force of friction on the player by the dirt. Okay, what other forces are acting on the baseball player? Well, we know there's gravity. There's a force of gravity acting downward. Okay. And now he's slowing, moving to the left and slowing, which means the net force has to be only acting to the right, which means there's got to be something canceling out his downward force. That would be a normal force, and that would be a normal force on the player by the dirt. And can I use hash marks? I can use hash marks for the up and down. Let's look at a force diagram for a girl who's stretching. Alright, so forces that are acting on the girl. If we were to draw a box around the girl, what forces are moving through the box, or cutting through the box? Well, like normal, we have gravity. Okay, I'm going to try to do this with drawing with the mouse, so it's not going to be beautiful. Alright, so we've got the force of gravity And I'm not going to put the feeler and the dealer on this. It's hard enough to draw what I did. So there's a force of gravity now. Oh, one thing we forgot, but we kind of took for granted, is she's not moving. So what does that tell me? Well, that tells me that the sum of the forces equal 0. All the forces balance. Ups and downs have to cancel. Lefts and rights have to cancel. Okay. And another force acting on her. Well, what's canceling out gravity would be the normal force on her feet, by the floor. So there's a normal force on the girl by the floor. Oops. Are there any forces left and right? Yes, there is. There's a contact force, a normal force, located here. So she's touching the wall, so that's a contact that's going through our box, if you will. In which way is that going to act? That is pushing her to the right. Okay, so that would be a normal force. Now something's got to be canceling out that normal force on the wall. Okay, this is the floor, and that's the wall. And this one is usually people struggle with until I say, what would happen to her? Would she still be standing like this if the floor was greased? And if you grease the floor, those feet would slip out and she would not be standing in that position. So that means we're missing a friction force. So that would be, and I did not put the feeler and dealer on these because it would be hard for me to write. But I will put hash marks and double hash marks. Okay. So these vectors, these force vectors that are at a diagonal, we can think of them as having x and y components. Just like when we launched a projectile at an angle, it had x and y components of its velocity. It is also useful to think of forces in terms of their x and y components, and you arrive at them the exact same way: sine, cosine, tangent, or Pythagorean theorem. So if I've got vectors like this, so I've got 3 vectors, and let's say that the object is at equilibrium, meaning all the forces have to cancel. Okay, I can go a little bit more detailed in this if I break the C up into its components. If I break it into an x component and a y component. So what I can do is say that my x components cancel with A, and my y components cancel with B. And this is useful for solving problems. Now, once I break this apart into x and y components, I don't use C anymore. Okay, I've used C by using Cx and Cy, so you don't double dip there. So if I've got a force, an object that's suspended from a ring and by a cable, then there's various components going on here. So we've got 2 tension vectors, and we've got the force of gravity going down. Now notice my left and my right have to cancel. My up and down have to cancel too, which means that these 2 would have to add up to equal this. Okay, and since the angles are the same, these would both be half of that. Okay. Let's see. This is going to be so hard without I guess I'll just do my best. So create a free body diagram for the crate, which is being pulled at a constant velocity along level ground. Okay. You'll have to bear with my drawing with the mouse, which is, I think, actually better than drawing with the stylus. So let's see. So the first thing I want to look at is, are the forces balanced or not? And it's moving at a constant speed along level ground. So the sum of the forces equals 0. All my forces cancel out. Okay. So let's label forces acting on the crate. So we've got the force of gravity going down. force of gravity on the crate by the Earth. There is a normal force. There's a normal force, and I should probably, oh no, I had to erase everything. Let's draw it again. There's a force of gravity, and there is a normal force. Now I didn't draw that as long intentionally. That's why I wanted to redraw that. So let's see. So it's sliding to the left. So we've got a force of tension upwards at an angle. Okay, and then we're missing one last force. Since it's being drug, there's going to be a force of friction, and friction is going to act opposite the motion. Force of friction. I wonder if I can change colors. I can. So now what I would know, if we call this ftx and this fty, I know that this would have to cancel with this. The x component of the tension would cancel with the frictional component, and then the y component plus the normal force would equal gravity. So that's what we would know. All right. We're almost done here. I know this one's running a little longer than I usually have them run, but stay with me for a little bit longer. Let's say we look at a box on an incline, on a hill, and it's stationary. The first thing I would know is, hey, my forces have got to cancel out. So there's a force of gravity down, there's a normal force acting up and to the right, perpendicular to the hill. That's what the normal force is, perpendicular. And then we'd be missing one force, wouldn't we? We'd be missing the force of friction. And now friction is acting up the slope. Okay? Now, if everything is right, if everything is balanced, then all these forces have to cancel. But I've got two forces at a diagonal. I could break this up into its components and that up into its components and say that these two add up to this and these two are equal. But there's an easier way of doing it. Okay, so what you're going to do is you're going to draw your vectors like you normally would. Okay, and we're going to consider the x axis to be down the slope. We're going to consider the x-axis to be down the slope. And we're going to rotate it so our x-axis, the slope, is flat. Okay, you literally like tilt the page of your like homework on your desk. Literally just tilt it. And if you do this right, your friction and normal forces will be straight up and down and left and right. And you only have one diagonal, and that would be your force of gravity. Okay. Now we're going to break it up into we're going to break gravity up into its components. Even though that's counterintuitive because gravity was straight down, we've changed the x-axis, so now it's down the ramp, and you'll see why in a second. Okay. So we're going to break gravity. Now, when you draw this, gravity should be your hypotenuse. Okay. So we've got your gravity in the y component should cancel out with your normal force. Okay, your force of gravity in the y component should cancel out with your normal force, and your force of gravity in the x component should cancel out with the force of friction. Okay, so now if I know this angle and I know gravity, I know everything. I can solve everything, and that's why it's very, very useful. Now, if there was no friction, some of the forces would not balance. Okay, and let's say I wanted to figure out the acceleration down the ramp, which would also be a very common problem. Okay, what I could do is use my page tilting method. Basically, if you have something sitting on an incline or that's rolling down a hill or down an incline, you're going to tilt the page. Okay, now we'll break apart gravity into its components again. We've got an FGX and an FGY. Okay, and this is down the slope. Okay, our FGY is going to cancel with our FN, and the net force is going to be this FGX component. And that should pretty much do it. Okay, Thanks for bearing with me through all that. 25 minutes. I know that was a long one. So work on the Freebody diagram or the Freebody diagram worksheet. I'll give you some time to do that. All right. Bye.